And I also want to point out, if you look at the orange squiggly outline, this one here and this one here, hidden inside of the poset, there are a lot of posets that you should be familiar with. If you start collapsing the variables on this side in every possible way, you get partitions of the number A. So there's a classical poset hiding inside of our poset. I'm sure there are many others, but that one in particular is kind of interesting. So I want to talk a little bit about the new results and what that buys us. So one of the things that I'm relatively proud of is the extremely fast, I'm trying not to brag, but the extremely fast computational tools for a fixed equation. Just as an example, I did a computation last night. It took 90 minutes. It checked 28 million colorings. It computed 2 trillion evaluations of the linear equation in question, and produced a certificate of the proof that was almost a gigabyte large. And in case 2 trillion divided by 90 minutes is not something you can do in your head, Wolfram Alpha informed me that that's one operation per 2.7 nanoseconds. So we're really using a lot of computational power to prove some of these numbers. There are also symbolic theorems. So we can use these computations to make conjectures. We can also use symbolic computations to automate that process, or to just give us more data, more generic data using symbols instead of fixed numbers. And by using this sort of organizational method, we can combine that in a more systematic way. Knowing something about this equation and this equation tells me a lot about that equation.
So you have computer proofs of things with symbols, not as numerical.
Yeah, we do. And the one thing it also helps us do is I've sort of put in blue boxes on the side here. I'll turn the light back on for just a second. I've highlighted the things that are not yet completely solved. So these families are very generic compared to some of the others. And those are the places where you want to push the envelope. That's the edge of current work. It's adjacent to, but not exactly equal to, stuff we already know. So I want to spend a couple minutes talking about the methodology behind proving some of these results. Originally, a lot of it was very on the spot. You just sort of came up with a proof, and if it worked, it worked. And if it didn't, you tried something else until eventually you got it. A lower bound is basically you give a valid coloring. So when we talked about the Shor number S3, we said 13 was not right because you could exhibit a coloring that does not have the property we want. It doesn't have a monochromatic solution. So that's what a lower bound is. I give you a coloring one less than the number I'm shooting for, and you check it, and if there are no monochromatic pairs or triples or whatever, then it has to be one bigger, at least. So that's why it witnesses an inequality, that the Rado number should be bigger than that. An upper bound is a little harder, it's a little more nuanced, because now I have to tell you every single coloring of that length has to have this property. This is an exists statement, this is a for all statement, right? So an upper bound is much harder. It's a lot easier when you don't have arbitrarily many variables. A lot of people have used direct proofs that valid colorings can't be that long by just arguing about the structure of the coloring. They'll often chase down elements that have to be red and blue. So I'll talk about how you would do that by an example. So S2 equals 5. So this is a very easy case. The lower bound is just on display. If I give you this coloring, the only possible red tuples that could fit are combinations of 1 and 4. And there's no way to take 1 plus 1 equals 4 or any such a thing. 2 plus 3, same deal. 2 plus 2 does not equal 3. But if I want to prove that S2 is less than or equal to 5, I could either check all of the possible colorings, which is actually not that hard in this case, or I could try to make a direct argument where I'm chasing down the colors of various elements. The number 1 is red without loss of generality. If it's blue, then change it to red. But because 1, 1, 2 is a solution to this equation, 2 could not possibly be red if I'm trying to avoid monochromatic solution. So 2 has to be blue. But if 2 is blue, 2 plus 2 equals 4, which forces 4 now to be red. And you basically just repeat this over and over again. You come up with a triple that has one odd guy out that you haven't talked about yet. We haven't talked about 3 yet, but 1 plus 3 equals 4. 3 has to be blue, 5 has to be red, 5 also has to be blue, which means 5 can't be included. That proves that 5 is too much. So that gives us an upper bound of 5. If it matches the lower bound, which it does, then we're done. So one thing you can do is you can do a lot of this in an automated way. So here is some output from a website I'll show you in a second. You can just go through and check all of the colorings one by one in sort of a systematic way. 1, 1, 2, 1, 2, 3, and you're looking to see where do you hit a problem. So 1, 2, 3 is a problem if they're all red. Here, 1, 2, 4 is a problem if they're all red. And you can just check them all. You can look at, I'm just going to show you everything here. You can look at the entire list of all the valid colorings. You can look at a tree that shows you all the valid colorings. So if you walk down this tree in any direction, you'll see a coloring that's valid. And the longest branch is 10, which means the Rado number is 11. Okay, and I'm just going to flip to this website. This actually comes from a website that I made with an REU student. So there, it's actually the same example. You can see that little tree that we had. So the website does all this in JavaScript, which is not fast, but it is pretty. And it's accessible on the web. So there's a way to do that as well. So the methods that we have tend to be ad hoc, at least at first. You make some guesses, you come up with some ansatz where you think you know what the guess should be, and you can get some lower bounds. Upper bounds, sometimes people pull some big tools from math, other math, but usually they're just directly proving what they're going for. There are also lots of constructive methods where mostly that's for the lower bounds. You can guess patterns, you can use randomized methods. Van der Waals theorem has some beautiful algebraic lower bound constructions. But most of the constructive methods for lower bounds tend to be an attempt to just push the lower bound a little further, not necessarily knowing when it's going to be correct. And the main thing that I've been using are brute force searches. You could try all of the possibilities, that's a little too much. But since you're searching a binary tree, like in the picture I showed, you just go along each branch until you can't go any further. There's also a way to sort of canonically reduce a tree search to a SAT problem. I haven't gotten into that, but I've been told that may be faster. We'll see. And there are also symbolic methods. Symbolic methods are just an adaptation of human proofs. Because all the human proofs here, very much in the Zauberger fashion, are just people doing the same thing over and over again when they should be asking the computer to do it for them. So one of the things that some of the methods I have used, they have sort of reproved entire papers worth of theorems automatically. And that's the kind of thing where symbolic computation really has a strong...
Hopefully you did a little bit more, let's say.
Yes. Those were lemmas and corollaries. So there's a lot of potential here. It's a little bit difficult because when you're solving equations and you're looking for integers, when you have symbolic parameters, you get rational numbers, you don't know which ones are integers, and that's where everything starts to get a little muddy. There are computational methods, where the small goal is to come up with a fast method, maybe one for the upper bound and lower bound, maybe one for each that's different. And one of the things that has a lot of potential is if you prove a lower bound here and an upper bound here, then everything in between is also governed by that. The entire interval in the post set, you now have upper and lower bounds on that. So the big goal is to automate this and to get a lot of this stuff automatic so that we can focus on the big picture, the structure, where do we want to prove the next theorems, how can we prove them. One of the things that will help us is interpolating a lot of this data. You can make lots and lots of numerical computations very quickly, and even if the symbolic computations are too hard, you have a lot of data, you can interpolate that. I think this is where I'm going to show you some of the data. So here I've got the equation 2x plus 2y plus kz equals 3w. So k is my only parameter. And if I import all of the data and I find an interpolating polynomial, here is a cubic polynomial. And for some reason in my heart, I think it should be cubic. But if I just interpolate the first three, it's obviously wrong. Because there it goes, it's missed the mark. But what we expect to see here is not just a cubic polynomial, but potentially a quasi-polynomial. So what I've got here are three parameters. D is the degree, P is the period, and O is the offset. So that should give me all possible quasi-polynomials that I'm looking for. And I'm interpolating this data set, which is not very big, but it's something. So if I think it has to be cubic, I'm going to go ahead and say cubic. Okay, so that was our wrong guess from a second ago. But if I change the period to 3, I like this one. I like it because, I'm going to say this and it's going to sound like I'm just making up or doing numerology, but the shape of that parabola looks like the shape of the data. Right? It has the same kind of bend. And if I interpolate out more points, every third point, hopefully, lies on this parabola. And what really hammers this home is when I change the offset, I also get those three. And when I change the offset again, I get the other three. So here, this kind of confirms my belief that it's cubic and that the period is 3. And if I were to go out and compute more data, I can be more and more sure that it's not a coincidence, right? Having 20 points on the same cubic is not a coincidence. 3 is a coincidence because you can do that regardless. But 4, 5, 6, it gets more and more certain as you go on. So just to conclude with a few open questions and comments. So Paul Erdős offered, I think there's money attached to this. I think I've given up hope of getting the money. But I'd like to continue to ask the question, since someone could get that money eventually, and maybe it'll be me one day. But this is, of course, a very famous integer equation, Diophantine equation. Pythagorean triples are a great set of numbers to study. And the question is, do they have this regularity property? It's a nonlinear equation. Most of our tools tell us nothing. Computationally, it's very difficult because these are distributed much more sparsely. Linear equations tend to have lots of solutions. If I take the numbers 1 through n, and I ask how many solution sets are there to some linear equation, it's order of n, roughly. Here, it's order of root n, roughly. I'm just ballparking this. So there are a lot fewer solutions, which means that if you run some tree searching algorithm, no matter how fast it is, it will jump out to a branch of length 200, 500, 1,000, at which point you could be checking up to 2 to the 1,000 different things as you search that tree. So that's a little too much even for the super fast methods that we have, so we want to rein that in somehow, and that's sort of one of the things I've thought about. Haven't had a lot of success, but faster and faster computers, at least that's getting us closer to the answer, if nothing else. The progress we've made So there are high-speed parallel algorithms. There are symbolic lower bounds we can prove, and ansatzes for constructing lower bounds. Just to give you an idea of what a lower bound ansatz would look like. The most common lower bound, and I use little r since it doesn't look too much like big R. I call this a sandwich, and of any lower bound, with different numbers of reds and blues, but of any lower bound you ever see, this is often the most common. And in a lot of cases, it's the only one, which tells us that there's something important here that you don't see with other colorings. That the extremal coloring in this case has a very strict structure. So that's an ansatz that's been very useful for a lot of people in an ad hoc context, and now we're trying to make it automated. Some of the upcoming stuff, ansatzes for upper bounds, which are a little bit harder to deal with, generating and analyzing these trees of valid colorings, looking to find new ansatzes for lower bounds, symbolic upper bound proving, and of course the sparse problems, which are very hard. Changing or tailoring the algorithms to suit those is quite difficult. I'm writing a survey paper. Included are all the results you saw in that big diagram, as well as my hope to conjecture and prove some of the boundary of that diagram, and sort of classify and add some structure to those results. I have lots and lots of data. If you want 10 terabytes of certificates, I would be happy to provide you with them. And I have lots and lots of tables that I'm currently interpolating to formulate conjectures. I also have a lot of partial results or sort of one-off results, lots of lower bounds. They're very easy to find. Some new ansatzes like the sandwich and others for getting those symbolically without searching the whole tree. I have some upper bounds, and I have some asymptotics. I alluded to this earlier, where it was k squared over whatever that other number was squared. So I have a proof of the lower bound, and I'm working on a proof of the upper bound, which is just an asymptotic, but that's certainly something. And I have a few conjectures about what it means to be 3 regular, but that's still one of the big open questions. What does it mean to be 3 regular? Rado completely classified regular and 2 regular, and we have necessary and sufficient conditions only for those. We know nothing about 3, 4, 5, 6 regular. What about systems? We don't even have conditions for 2 regularity. Nonlinear is just Pandora's box. And we can look at different classes of linear equations. And one thing that's missing, which we have in most other Ramsey Theoretic contexts, are recurrences and inequalities like this, where E1 and E2 depend on E somehow. I don't know how you would get that, but that would be a huge breakthrough. So that's all I have. Thank you very much.
Time for a quick question. And is it possible to use a methodology to redo the kind of the deep similarity and Ross theorems?
Maybe. I'm not sure. Part of what most of these methods rely on is the fact that you have multiple color classes, and you sort of go back and forth between them. If this is red, then this is blue, then this is red, then this is blue. So trying to prove something about a set of a particular density, maybe you could do it in the sense that you'd just be arguing the Ramsey theoretic perspective and then trying to lift that to the density type results, but I'm not sure if any of these methods would directly apply to that.